We talked about the method for building models previously, and today we are going to talk about the type of models, right? What are the type of models? I illustrated that the models are, they're quite similar to the systems we talked about, like discrete and continuous and open and closed, static and dynamic and deterministic and stochastic models. And they're quite similar and quite easy to understand because if you have a stochastic system, if we made the model for that system, it is going to be a stochastic model. So let's start and choose some different colors this time. So we have continuous versus discrete models. They are described systems, right? So I talked about the systems where changes occur smoothly over time in mechanical systems or population dynamics, right? We turned about the continuous weather, systems like weather, right? If I make a model for a weather system, then it would be a continuous model, right? And they also give examples of like mechanical systems related with mechanical engineering or the population dynamics, of how the population is continuously changing and increasing or decreasing, whatever, right? Discrete models capture systems that change at specific intervals like queuing systems or digital communication. So you get more and more examples to really think about these two things or these models and systems. Models are nothing but the systems we make models for are, okay, let me put it simply. For example, I have a continuous system. I make model for that continuous system and become continuous model. Simple, easy. So we're going to go through it really fast. We have static and dynamic, and static models provide a snapshot of the system at a particular time, like equilibrium models in thermodynamics, because static doesn't have any change. So they just give for a particular time, for all the time they remain same. That's why it just give the snapshot. Snapshot means just a look around, like Snapchat. Dynamic models, they describe how the system evolves, like simulations of traffic flow. We're getting more and more examples. Really going to be helpful while you're writing about them, right? And so you should read them about and write them down. The static models are equilibrium models in thermodynamics, like in heat flow systems. I don't know much about it, but they do remain the same. That I think it is the where the heat I think it was some like exothermic or endothermic, where the heat going is equal to the heat released, so there's no change in there. And then the dynamic models, we have simulation of the traffic flow, which is always like changing. Then we have deterministic and stochastic models. They provide precise predictions based on initial conditions, like solving equations for a chemical reaction. Great. Stochastic models include randomness, like modeling disease spread in population. So we have to randomly really kind of simulate the disease. For example, for COVID, there were techniques used to they simulated how much the disease is spread in populations. And of course, the solving equations can go for deterministic because we already know the initial one. So we can know we have H2 and then also we have O2. We know the initial conditions. We know that it's going to be 2H2, right? You can balance the equation. Black box versus white box model. What that means, it's something new. So black box models focus only on inputs and outputs without considering the internal workings of the system. Machine learning models that predict outcomes without a deep understanding of the underlying mechanisms themselves. So once a time I asked ChatGPT, how did you made yourself? Like how the company made you, something like that. Or, who made you, right? I think it was newly released. At that time, he didn't tell me that. You could ask it that who made ChatGPT. He would ask like OpenAI's, right? But you can't just directly ask him who made you because he doesn't really know about it. Maybe he does now, but at that time he doesn't. So in the black box models, we just focus on the main purpose of the system, right? For the machine learning models, we really focus on the main purpose and not these underlying details that, like for the ChatGPT, we have really the computations and the neural networks and all those um, links of generating the data and accessing the data in the GPT. But here we have kind of, where we only focus on this, what is this going here and what is getting out, without really considering the internal workings of the system. White box models involve detailed knowledge of the system internal structure and mechanisms. Physical simulations most of the time where the underlying physics is known. I gave you an example of the pendulum earlier in the video, I think in the previous video, where we talked about like how they, how we basically simulate the motion of the pendulum uh, in terms of the tension and the force and that Newton's law. In that case, there would be, the physics is known. We have some setup in which we use to do this experiment. In the black box, we only focus on inputs and outputs, but in the white box, we focus on the internal work, right? So these were some models. I think this was only the new one. We have discussed about the other systems, so it's really easy to get what these models are. Okay, so model building in relation to simulation. So we have studied about the steps of model building. This is a little bit exaggeration of that same thing, and we are going to go over that one by one, right? So let's start model building in relation to simulation. Okay. Model building is essential preparatory system for simulation. Okay. And with now, I think this is not the point. Okay, sorry. So this is in turn of a simulation, but the steps are going to be detailed next, which we're going to study sooner. I thought this was that topic, but this is actually in terms of the relationship to simulation. Model as a blueprint for simulation. Like we talked about class. So what is a class in OOP or object-oriented program? It's a blueprint for an object, like a page where you write some details and then you have some object that can refer to it. Then you can have many objects that can refer to the same page or same class in this case. So a model is the blueprint for simulation. In other words, you can have a blueprint, right? You have the simulation blueprint, and at a certain point, you would have bunch of simulation variables. You have this variable and this variable, but they all are going to be applied to this blueprint, right? So we kind of create a blueprint for a simulation where we can change different things to analyze different outcomes. The model is the structured representation of the system, and the simulation is the execution of this model over time to observe behavior. Okay, the quality does impact the simulation. Efficiency in problem solving. A well-built model simplifies complex systems, making simulations more computationally efficient and easier to interpret. Like, they would give an example that if we, for the lumped, we talked about the lumped systems, and we talked about that they focus only on time and not on space. In that case, this is that we can easily choose the parameters in the lumped in thermal systems, like for the heat, where the time is constantly changing, but space is not the main point there, right? And then we have iterative process, meaning we are always refining our models. Like the ChatGPT came out and now the like photo and then photo mini and then I don't know what and what. Like there are a lot of coming out and they are adding always the new features, right? So these are all the updates that you make to your model, right? Then we have, this is not important, and then so this was what I was talking about, the methodology of the model building. These are the same steps that we have talked about earlier, but they are just even more explanation and simplified. So first we talk about the defining the problem. In that step, what system or process is being modeled, what specific questions need to be answered by the model, what are the expected outputs to solve from the model. So in the problem definition, we need to clearly define the problem we are trying to solve, and we need to ask these three questions. Which system or process is being modeled? In other words, I told you the specs of the system. what specific questions should the model answer, or what specific problem does the model answer, and what the output it should show, right? So it's also defined the scope. So we have kind of understood it in the previous video, but this is just kind of more, detailed system. We talked about conceptualization, real-world systems as a model, where we talk about that how can we conceptualize the real-world system as a model. We define the model and then we conceptualize into key components where we have state variables, subsystems and interactions, and input-outputs, etc. What are state variables? They are quantities that describe the system's current state, such as temperature, velocity, or population. Always remember the state variable definition, because state variables are going to be using it a lot of context. So they are the quantities that describe the system's current state. And then system boundaries, which separates the system from its environment, right? Then we had data collection and analysis, but on that in the previous video we studied about choosing the model after a step, but there's one more step here, an additional step. Before building a formal model, it's crucial to gather relevant data about the system. It can include historical data, it can be experimental data, or it can be theoretical data like constants, laws, principles from existing scientific literature. Mostly in physics, I think, we do this kind of stuff so that we can get hypotheses right. And data collection helps in understanding the system's behavior, identify trends, and validate assumptions, right? I told about the hypothesis, right? Because when we're trying to find some experiment, we first need to give some deduction and hypothesis of what can possibly be happen. So it's good to have some knowledge about the system, right? And then there comes the fourth part. So there's this additional step where we get the historical, experimental, and theoretical data about the model. Now we need to choose the model. We can choose deterministic model, or stochastic, or continuous, or discrete. Now fluid dynamics is always coming in your in these notes, but they are basically related in physics, where you have kind of how the liquid flows, or chemistry maybe. I think the soluble, solute, solvent stuff. I think that this is what covers in these topics, but you can always search more about them. Okay, and then we have discrete models, right? Population growth in yearly increments, right? So population growth dynamically, we talked about that this was continuous because population growth is continuously changing. But if we talk about like population growth in yearly increments, like after, for example, 2 years, or 4 years, or 6 or 8, then it will become a discrete model, right? And then we are going to formulate our model. We can use it by mathematical or state transition models or agent-based models. You can even read about Newton's law of motions when we use to represent mechanical systems, traffic lights, or cellular. Yeah, this one. Read this. State transition models for systems that operate in distinct states, such as traffic lights or cellular automata. This approach defines how the system moves between different states. Agent-based models is used to simulate the actions of individual agents within a system. Then we use the parameter estimation, determine the value of key parameters that will drive a system's behavior, and they could be constants, they could be coefficients, like rate constants in chemical reactions. You may have heard about RK, or RL, something like that, or growth rates in population models. We also measure the probability of the population increase and friction coefficients in mechanical models, like F, something like that. Right, so you can talk about all the constants that you have read in physics, chemistry, and statistics. Okay. Parameter estimation is often done by analyzing historical and parameter experimental data and fitting the model to this data. Statistical methods such as regression analysis are commonly used. Model calibration, fine-tuning the model to make sure it aligns with real-world behavior, comparing the model's prediction with known data, adjusting parameters or assumptions to reduce discrepancies between the model output and the observed data. So we may adjust the parameters, and discrepancies mean any sort of disturbance or misunderstanding or confusion. Calibration ensures, okay, and then we have model validation with the process of verifying that the model accurately represents the real world system, right? So this is just the fine tuning, right? Okay, baby's good in the home, but what about when if he really goes to tell the teacher what he learned, right? So this is done by testing the model's output against independent data sets or known behavior. If it provides accurate and consistent predictions within the cost of the problem, it holds up against new unseen data, right? So for example, they use ChatGPT to test with the new data it wasn't trained with, so it becomes more valuable to get insights on how it performs and their proper charts to kind of see the working of each LLM, right? You can search them up on Google. Okay. It provides accurate and consistent predictions, and it holds up against new unseen data. And then we do simulation, test different what-if scenarios, experiment with system inputs, initial conditions or parameters, analyze the potential outcomes or consequences, right? Analyzation and interpretation, looking for trends, patterns, or behaviors in simulation results, right? Comparing the simulation outcomes with real world, drawing conclusions, or making recommendations. So analysis, I told you, was simply to see that how this interpretation was to see how the simulation is performing, how the system is performing, or the model is performing. Analysis to see how it does, work in the real world. And then refinement, adding more details like simplifying the model, re-estimating parameters, or recalibrating the model, right? And we haven't talked about this one where we document it, and model and report the results where we write the documentation, we result of their estimation, and the conclusions drawn from it. Everything is documented. So these were all the methods with some little, additions to it. You can look even more into them, and in the next video we will look into the model and experiment description, or in other words the analysis of the experiments or the simulations, right?